Let us start with the third problem. So G is a group, G is a set with three elements, one omega and omega square, where omega is a primitive cube root of unity, and we want to show that this G is a group with respect to usual multiplication. Now omega is the cube root of unity, so we know that omega cube is equal to 1, that is because omega is the cube root of unity. So omega cube minus 1 is 0, and this factorizes into omega minus 1 into omega square plus omega plus 1 equal to 0. Now omega minus 1 is not equal to 0 because omega is a primitive cube root of unity. This means that omega square plus omega plus 1 is equal to 0, and solving this equation, quadratic equation, we will get omega is minus 1 plus or minus I root 3 divided by 2. So we will take omega as minus 1 plus I root 3 divided by 2, and omega square, if we calculate, will come up to be minus 1 minus I root 3 upon 2. So we will do this calculation. You can do this calculation in your leisure time. So if I plot this number, complex number, minus 1 plus I root 3 divided by 2, this number is here at an angle of 120 degrees. So this is omega, and this is omega square, which is minus 1 minus I root 3 divided by 2. So these are the three numbers, 1, omega and omega square. They are of G. Now we will take these elements and prepare a table of complex multiplication. So when I go for the first part of this set, if I say closure, I am going to take 1 omega square with multiplication as 1 omega square. When I multiply that, I'm going to get 1 into 1 is 1 omega square. Again omega into 1 is omega into omega is omega square, omega into omega square is omega cube, but omega cubed is 1, so I will write a 1 here. Then omega square multiplied by 1 is again omega square. Omega square into omega will be omega cube, which will be 1. And omega square into omega square, what is omega square into omega square? It is omega raised to 4, but omega raised to 4 is omega cube into omega, and omega cube is 1. So this will remain only omega. So here you get omega. So this table shows you that all the entries in this table are 1 omega and omega square. So given any A here and given any B here, what is A star B? A star B is this table, values in the table. They are again in the same set G. So the table shows that the set is closed under complex multiplication. So let me erase this. So therefore G is closed. Therefore G is closed under multiplication. Now the second thing is associativity, which I will again leave it as an exercise for you to check that A star B star C is equal to A star B star C. Associativity can be checked. Third thing is identity. So here I clearly see that any element multiplied by 1 is giving me the same element. Omega into 1 is again omega, and omega square into omega 1 is also equal to omega square. So obviously identity of this set is 1, because I multiply 1 with anybody, I will get the same thing back. Fourth is inverse. So let us write the elements and let us note down their inverses. So elements are 1, omega and omega square. From the table I see that 1 into 1 is 1, omega into omega square is 1, and omega square into omega is also 1. So this means that 1 into 1 is 1. Omega into omega square is identity, which is 1. Therefore, inverse of omega is omega squared. And omega square into omega is also equal to identity, which is 1. So, inverse of omega square is omega. So, this means that all elements in my G, 1 omega omega square, have inverses also. I have identity also, associativity is also there, and G is also closed under multiplication. This means that G is a group. So this finishes our third exercise.